The Mach number is very useful for determining what compressible effects will occur in a flow. But to determine the Mach number, we first need to be able to calculate the speed of sound. We all have some intuition about how fast sound travels. The delay between seeing the flash of lightning and hearing the sound of thunder is due to the speed of sound being far slower than the speed of light. But how do we compute it exactly? To begin to answer this question, let's start with the definition of the speed of sound. It's the propagation speed of a wave of infinitesimal strength, one where the pressure variation across it is a tiny fraction of ambient pressure. Let's consider a plane compression wave of this type, with frontal area A propagating to the left with speed c. Upstream of the wave, the fluid has pressure P, density ρ, temperature T, and is at rest, so the velocity v equals 0. Downstream of the wave, all quantities are increased by small increments denoted with a delta. In this reference frame, the wave is moving, making it slightly more difficult to analyse. To make things easier, let's change to a reference frame that moves with the wave. To do this, we add a velocity c to both the wave and the fluid to its left and right. In this new reference frame, the wave is fixed and thus the flow is steady. The flow from the left travels towards the wave with speed c, and the flow to the right departs with speed c minus delta v. In the next module, we'll derive an expression for the speed of sound by placing a control volume around the wave and applying conservation of mass and momentum.